Hello, my name is Joaquín Julve. I'm a PhD student here at Núcleo Milenio Ciclo and Precursor Project. And the title of my research is called Crustal Fault Dynamics through the Subduction Seismic Cycle, Unraveling the Liquiñe-Ofqui fault system case. As an introduction, I would like to start showing you the study area where we have, or where it occurred, actually, the Valdivia earthquake in 1960, that according to some numerical models, it released nearly to 45 meters of seismic deformation. And it actually occurred in a very complex tectonic setting where we have first the subduction zone, the Liquiñe-Ofqui fault system, which is a major structural feature that has an dextral kinematics, so it's a strike-slip system of faults that is right beneath the volcanic arc, the active volcanic arc, which you can see here in red triangles, and in the northern part is limited by the Lenalwe fault, which is another major structure that has a sinestral kinematic. And along with the Liquiñe-Ofqui and the subduction, it defines a 4-arc sliver, which is called the Chiloé sliver, that according to some previous work has an anti-clockwise rotation. So actually, in this context, what we want to do is to try to define if there is a relationship between the megathrust dynamics right here and the continental crustal faults related to subduction zones, which is the case for the Liquiñe-Ofqui fault system. So if there is a relationship, the idea is try to define how is the behavior of this structure just before, during, and after some big earthquakes, and that's because there has been observations of active seismicity in this fault in these periods of time. So there are actually a manifestation of a possible relationship between these two structures. So we know that the megathrust has a very complex distribution of some frictional parameters, as you can see here, and as it was defined before by some previous authors, such as Weiss in 2019, and that actually will define how this fault will behave through the subduction seismic cycle. Also, the idea is to assess the role of the viscoelasticity in the deformation, in the crustal deformation, but also in the activity or the dynamic in this subduction fault. So in order to establish a very complex model of how is the dynamics of the megathrust related to the dynamics of the Liquiñe-Ofqui fault system. In terms of the methodology, we are going to use two approximations. The first one is a quasi-dynamic modeling, where we're going to assume that the fault behaves following a rate and stage friction law, using the code Unicycle, which was made by Sylvain Barbot, which is a collaborator of us from the University of Southern California. And here are some results from that code, where you can actually see how is the evolution of the velocity through the time of simulation that actually describe quite well the different periods that are happening in the seismic cycle. So when the velocity is at steady state, we are looking at the interseismic. When the fault speeds up, we are looking at the coseismic right here. And when the velocity is come back to a steady state value in a very long period of time, we're looking at the poseismic phase. And here in the plot below, we have the cumulative slip at each event. The second approximation will be a kinematic modeling, where we are going to estimate the velocity field. And this is an example of the work of Marcos Moreno in 2011. And the idea is to compute or to obtain the locking degree at this segment of the subduction fault to actually constrain the distribution of some frictional parameters of the rate and stage friction law in order to have better results. In terms of the data, we have 42 continuous GPS, and we want to remeasure 35 spots with surveyed GPS stations, which are the ones in yellow colors here. In terms of the thermal model that describes the temperature distribution of the continental lithosphere, we have some thermal distribution for all the continental lithosphere, and the idea is to use that in order to estimate the viscoelasticity in the continental and the oceanic mantle. Well, finally, I want to show you some preliminary results. So here we have a configuration of 2D setup where we have the continental and oceanic mantle and some very simplified geometry of the subduction fault that is behaving following this equation, which is rate and stage friction law formulated by Sylvain in 2019. I'm not going to describe in so much detail, but the basic idea is that we have a shear stress related to some coefficient of friction to some effective nominal stress on the velocity in the fault with respect to some reference value, and some adimensional parameters that actually are going to define how the fault will behave in time. So this is a result where we have the depth in the fault, the time of simulation, and the changes are representing changes in the velocity in the fault through time. And when the changes are very limited into a straight line right here in a very short period of time, it means that we are looking at a very great earthquake. You can see that the rupture propagates from the up dip until the down dip limit. And we have some very complex mechanism of velocity here in between some very major ruptures. But the idea is that you can actually describe some very complex situations that are happening through the seismic cycle. I'm not going into much detail about this because, of course, it's not time for that, but that's the idea. So thank you for your attention. Goodbye.